Hello and welcome back to the pharmacology session, and today we are taking a deep dive into the drug's journey through our body, metabolism, also known as biotransformation. This is where our body's internal chemists work together, transforming the drugs to make them easier to eliminate. It's truly a marvel of biological engineering. As we discussed, many drugs are lipid soluble. They are greasy and don't mix well with the water. This is great for getting them to across the membrane to their targets, but it's terrible for getting them out of the body, as the kidneys primarily excrete water soluble substances. So the liver mainly sets up as our body's primary chemical modification and detox lab. Its mission is to take these lipid soluble drugs more water soluble so that they can be flushed out. Imagine a highly specialized recycling plant. Drugs arrive as large, oily, difficult to handle waste. The plant's job is to break them down into smaller, more manageable pieces and then attach handles or labels to them, making them easier for waste disposal trucks to pick up and remove. So this process happens in two main phases, phase 1 and phase 2. So the phase 1 reaction is the rough cutting. It's like the initial rough cutting stage in our recycling plant. They introduce or expose reactive functional groups on the drug molecule, making it a bit more polar and ready for the next phase. So here oxidation, so this is the common phase 1 reaction. It involves adding of oxygen or removing hydrogen from the drug molecule. Think of taking a large complex piece of oil waste and using a plasma torch to burn some of the grease or create a small reactive hook on its side. So the enzymes, it's cytochrome P450. It's the cytochrome P450 monooxygenase system actually, and it has vast subtypes too. So these specializes in metabolizing a specific set of drugs. So all these subtypes, they are like different specialized cutting tools in our recycling plant. And then we have reduction. It's the opposite of oxidation, adding hydrogen or removing oxygen. Then we have hydrolysis. This involves breaking down drug molecule by adding water, like using a high water jet to break apart some waste. Other enzymes beyond 450 are esterases and amidases. So these are also involved in hydrolysis, breaking down drugs like local anesthetics or muscle relaxants. So outcomes more active than the original drug. So the metabolite is going to be more active than the original drug, and it may be less active than the original drug too. So this is the most commonest path, and it might be completely inactive or it might turn even more toxic too if something goes wrong. Phase 2 reactions, the handle attaching, that is the conjugation or addition of synthetics. So phase 2 reactions are handle attaching stages. These are synthetic reactions where a large polar molecule is covalently attached or conjugated to the drug or its phase 1 metabolite. This makes the drug much more water soluble and usually inactive, perfectly set up for excretion. So taking the slightly modified pieces of waste from the phase 1 and firmly attaching brightly colored water soluble handles or labels like large sugar molecules or sulfate groups, so the disposal trucks can easily identify and carry them away. So we have reactions like glucouridation, acetylation, glutathione conjugation, glycine conjugation, sulfation, methylation. So all of these, they help in addition of handles. So glucouridation, here we add glucouronic acid, and is the commonest thing, making the drug very water soluble. Then acetylation, we add acetyl group. Glutathione, we add glutathione. It's important for detoxifying the reactive or toxic metabolites. And glycine conjugation, attaching glycine. Sulfation, we attach sulfite. Methylation, we attach a methyl group. So the outcome metabolites are always much more water soluble and pharmacologically inactive, ready to be excreted primarily by kidneys or bile. And then we have factors affecting drug metabolism. So while our body's detox lab is incredibly efficient, its activity isn't constant. Many factors can change how quickly or slowly drugs are metabolized. So we have genetic factors, polymorphisms. We're all built a little differently thanks to our genes. Small variations in genes that code for metabolic enzymes, especially our cytochrome P450s, are called polymorphisms. So let's imagine them like small chemical workers. Some are naturally fast workers because of their genetics, and while the others are slow. So this explains why some people are rapid metabolizers where the others are poor metabolizers. For example, a significant portion of South Asian population, including here people in Chennai, might have genetic variations that affect how they metabolize certain drugs, making a personalized dosing crucial. That is where precision medicine comes into play. And we have factors like age, sex, and liver diseases. So children and elders have reduced metabolic capacity, and hormonal difference among men and women can lead to subtle variations in the metabolism. And liver diseases, it's a big one. If the liver is damaged, like cirrhosis or hepatitis, the detox lab is severely compromised. This means drugs aren't metabolized efficiently, leading to drug accumulation and potential toxicity. And nutrition, so malnutrition can impair the enzyme function too. Then we have drug-drug interactions. One drug can directly impact the metabolism of the other. So we have enzyme induction. Some drugs or environmental factors like smoking can increase the activity of number of metabolic enzymes. So it's like turning up the speed of a recycle plant, cutting tools, or hiring more chemical workers. So clinically we have phenobarbital. It can induce cytochrome P450 enzymes. If a patient is on warfarin, a blood thinner, and also takes phenobarbital, the warfarin is broken down much faster, making it less effective and increasing the risk of blood clots. And so they do not prescribe phenobarbital and warfarins together. And we have enzyme inhibition too. So some drugs can inhibit or decrease the activity of metabolic enzymes. It's like slowing down our own chemical workers or even putting a wrench in their machinery. For say, grapefruit juice inhibits a specific cytochrome P450 enzyme in the gut. If you drink grapefruit juice while taking certain medications like statins or calcium channel blockers, the drug isn't broken down as much, leading to dangerously high levels and increased side effects. That is, the drug doesn't work properly. And what it all means for our health. So understanding the drug metabolism isn't just academic, it has profound clinical implications too. So bioactivation, prodrugs. Sometimes a drug is given in inactive form called as prodrug, like our levodopa. It only becomes active after it's metabolized. Like, I think levodopa is not exactly, it doesn't exactly come here. So think of it like delivering a flat packed piece of furniture that only becomes functional once you assemble it. So codeine is a prodrug that needs to be metabolized by cytochrome P450 into morphine to exert its pain relieving effects. Genetic variations can even affect this conversion. And we have toxic metabolites too. Metabolism doesn't always lead to harmless products. Some drugs can produce highly reactive or toxic metabolites, which can cause organ damage. For say, high doses of paracetamol can produce a toxic metabolite, if not detoxified by glutathione, can severely damage the liver. And we have first pass effect. So we have touched on this repeatedly, but it bears repeating. For many orally administered drugs, a significant portion is metabolized by the liver before reaching the general circulation. This reduces its bioavailability. For say, drugs with high first pass effect often needs to be given in higher oral doses than if they were given through IV, or they might not be given orally at all. And there you have it, a deep dive into the incredible world of drug metabolism. It's a complex dynamic process, but that's cool too, understanding the liver. And that's it for the day.